Hello, everyone. Welcome to another exciting episode of The Life Chronicles. I'm your host, Simon William, and today it is another beautiful day with a beautiful weather outside here in Melbourne. And actually, it is so amazing. Yesterday, I was watching a news, and it was all about climate change issues. But most important, there is the session that managed to caught my attention, and that session was more into thunderstorms and how difficult they are to be predictable and all the problem that they cause around the world. That thing actually caused me to dig a little bit deeper, trying to understand a little bit of some fascinating facts about thunderstorms. For example, I didn't knew until yesterday that around the world, in each and every moment, there are about 2,000 thunderstorms happening at the moment, every time around the world. And here's the most fascinating fact is that a single lightning bolt can reach up to more than 30,000 degrees Celsius heat, which is almost 5 times hotter than the sun's surface. And apparently what was shocking is to understand that around 10 to 15 wildfires around the world actually are caused by thunderstorms. And there are so many things that I think we need to understand about these matters here. We need to understand, for example, about climate change, extreme weather events. How do they relate with thunderstorms? If we are talking about extreme weather, does the thunderstorm nowadays become more extreme than they used to be? How are they predicted? Different kind of technologies and everything. And I was struggling to find a person who can just sit down with me and we can have a chit chat about thunderstorms. And luckily enough, a friend of mine just came into my mind, and I remember I have a colleague of mine who actually spent his time learning a lot about thunderstorms. Ladies and gentlemen, I would like to welcome Ewan. He is a research fellow in atmospheric science at the University of Melbourne. He is currently developing computer programs for tracking and analyzing thunderstorms in observation and simulation data set. Now, these computer programs actually provide different kind of insights into thunderstorm process and facilitate assessment of whether these processes are simulated correctly in weather forecasting and climate models. Now, his current project actually aimed to develop the better understanding of the relationship between thunderstorms and the aviation turbulence. He has done his PhD at the University of Melbourne, Department of Science, Geography and Atmospheric Science, and he got his undergrad at Adelaide University, focusing more on mathematics and computer science. Ladies and gentlemen, please welcome my friend, my brother, my colleague, Dr. Ewan.
Oh, thanks, Simon. What a lovely introduction. It's great to be here chatting with you.
I was just trying to put some facts together, and apparently these are very shocking things to me about concerning thunderstorms. But I have a question. Atmospheric science, it's a huge field. What happened to you that you choose, okay, let me focus, studying thunderstorms?
Well, it was more just random chain of events, really. I started in mathematical science because I really liked the idea of simulating complex processes using mathematics. And then I drifted into meteorology because that's one of the main applications of fluid mechanics, which is a type of applied mathematics. And from there, I drifted into thunderstorms. So it wasn't like I set out to study thunderstorms. I just kind of ended up here. But I'm glad that I did. It's a very engaging topic.
So did you choose it, or you think it chose you?
I think it chose me, yeah. I think that I started in meteorology and I initially wanted to do more the weather forecasting side of things because I wanted to get a job at the Bureau of Meteorology as a forecaster. So when I came to Melbourne, I was studying more the weather end of things, and then there's a group here led by Todd Lane that focuses on quite small-scale meteorology. So individual storm clouds, individual cloud processes, small-scale phenomena within the atmosphere. I think that's the way it goes for a lot of students. You don't necessarily know where you're going to land because you don't necessarily know the full details of a field when you started in it. But yeah, I think it's a really fun topic.
Let me just give you an example. For example, when we were just talking about sometimes something choose you, or sometimes the way you ended up on something, and then at the end of the day, you start asking yourself questions. How on earth I chose to be here? For example, I'm dealing with that. It's the same thing. It's a branch of atmospheric science, not more into air quality. But the way I wanted it to be, it's a little bit different. I remember this time, it was the first time getting to class, and the professor walked in, and we had some chit-chat discussion and everything, and then he put a video, actually. So he didn't want to spend most of the time teaching, since we knew nothing at the time. We were just freshmen, fresh from high school, and then just all of a sudden, just, okay, let us sit down and then listen. And he told us, okay, I want you to listen carefully. Watch this video, listen, and I want you to write a report out of it. Everybody was just like, yeah, this is going to be an easy and fun class. Watching some videos, write a report, all good to go. Here's the funny thing. The video was about what will happen if the temperature reached up to 1.5 degrees. I think it was produced by BBC, something like that. So when I started listening to it, and I was like, wow, these are very fascinating stuff. And I began to just, it catch my attention. And I said, you know what? I'm going to find this professor at the end of the class, and I want to have some time, talk to him. And I want to spend more time learning these stuffs. So I remember after the class, I walked toward him, and I told him, Professor, I liked it. And I really, really want to find myself, in atmospheric science. I just want to know more about climate change. And he asked me, so what can you do? I said, I don't know. I like talking. I just want to spend more time educating people about climate issues. He says, okay, just come to my office. So the next day, I walked towards him, to his office, just a little bit talking and everything. And he handed over the book. The book was just written, Global Warming. Oh. I was like, okay, let me just go and dig deep. So I started it, and he just gave me a challenge. He liked the way I was, my attitude, eager to learn, get some new information, always pushing forward. So at the first, I thought like he was kind of ignoring me. So every time he told me, once you finish one chapter, you can present, and then we give you another chapter. And I want you to spend more time like you're talking to the general audience, people who know nothing about climate issues. And I want you to educate them based on what you've learned from the chapter that you've read. I was like, okay, fun thing. So at the end of the day, I was a little bit busy, working part-times and everything. And all of a sudden, he called me one day. He says, you know what? I want you to stop working outside. I want to give you a job.
Oh, fantastic.
What kind of job? He told me the job is, I want you to go and study, and I will pay you for you to study.
Really?
Yeah.
That's fantastic.
Okay. Sounds good to me. So I treated it like a job. But for him, I don't know, but he wanted to get something out of me. So I finished the whole book, about 500 and some pages. I finished all of it. He called me, we had lunch, and he told me, so we've studied about climate change, CO2 levels and everything, but do you want to know the real deal? I said, what is it? He says, I want to take you to the bottom of the problem. And it's all about emissions, air pollution, all that kind of stuff. Do you want to learn about it? He says, yeah. And then he started put me closer to him, and I started learning about air quality, air pollution, and I was like, wow, this is so good. Here I am today doing my PhD in air quality. I'm not so sure. Do you have the same experience, something like that ended up you feel like, you know what? I will go and Thunderstorm have some really fun, fascinating facts.
Absolutely.
Try something like this. How was it from you?
Yeah, it was similar. Well, like I said, I kind of drifted into it, but once I was there, I definitely felt that's where I wanted to be. So it's interesting you mentioned before about air quality. Thunderstorm processes the strong vertical updrafts that are associated with thunderstorm type clouds. They actually play a leading role in ventilating the air in the lower atmosphere. So they're lifting up a lot of the polluted air that we get near the surface. They're carrying that up to the upper levels of the atmosphere. And they can also bring air from upper levels down to the surface. So they play a role even in something as immediate as air quality. As to that feeling of landing somewhere where it feels like you kind of that field chose you. I remember when I was a kid, I really loved all the mythologies, different mythologies of the world, like Zeus.
The most funny thing is when I was just yesterday when I was just putting together some facts.
Yeah,
and you sent me the message, and you showed me about there are different mythology, different countries, different civilization. People associated these things like with the deities.
Yes,
I want to know more about that one.
I think it's really interesting. The thing that I first encountered was as a kid, growing up in the West in Australia, I was given a lot of books on Greek mythology. So we learn about, Zeus and all those Greek gods. Certainly Zeus was, the god who threw the lightning bolts around. Then I learnt a bit about the sort of Viking, Scandinavian mythology, with Thor, and obviously Thor's now a popular figure because of the superheroes and all that. But if you actually go to the Wikipedia page on storm deities, it'd be easier to list the cultures that don't have a storm deity, because it seems like almost everywhere has one. So in China, for example, in Taiwan, you'll find temples with statues of a deity called Dianmu, and she was imagined as a woman holding mirrors, and the concept was she's kind of reflecting light down to the surface, and that's the lightning bolts. And I think she also has a kind of like a husband type figure. I forget the husband's name, and they kind of battle in the sky, and that's what makes the thunder. So I think that even in Australia, so there's an art exhibition I saw in Melbourne, and it had a lot of art from the Aboriginal people of northeastern Australia, the Yolngu, and there was one painting about the deity was called, I'm probably pronouncing it wrong, but Bolngu the Thunderman, and it was this beautiful image of this deity sort of raining down on the northern part of Australia, and
it's called Yolngu. Something like that.
Yolngu, that's right. And so that image was associated with the Northern Australian monsoon, which is a part of the year where it becomes really wet, and there's a lot of thunderstorms. You get the monsoon coming through, and a lot of thunderstorm processes occurring through Northern Australia. So I think that the phenomena is really captivating. It's captivated the human imagination for thousands of years, and I sort of feel like I'm in that sort of tradition in a sense.
That was a time I really like to search and get some different information, just learning about different ancient civilizations, ancient cultures, and how they live their life, beliefs, science, and everything. And I come across with something, the way we're talking about mythology and everything. And the thing is that during the ancient period, most of the time, people tried to find a way that they could connect to the source of life, to connect to God.
Yeah.
And oftentimes, people, they used to associate different natural phenomena with deities and something like that. And since we are on a thunderstorm, these are just 10 different culture that used to associate. I think there are still some of the culture that do the same thing.
Yeah.
For example, there is the Norse mythology, Scandinavia, Thor.
Yeah, that's right. Yeah.
There is the Greek mythology, which is Zeus, Roman, Jupiter, which is similar to them. There is a Hindu, which is called Indra.
Yeah. Wow.
The god of storm, the god of storms. And then there is a Slavic mythology, which is Eastern European, Perun. There is the Yoruba in Africa, Shango. They call the god of thunder, lightnings, and fire. And then there is the Aztec, which is Tlaloc, the god of rain, water, and fertility. In the Japanese, there is Regin, the god of thunder and lightnings, as you were just explaining. And so, like a Maori, Baltic mythology, Celtic, Aboriginal Australia.
Yeah.
So the thing is, even back in the days, people used to like to understand about natural phenomena, but they find a way that to put it
exactly
based on their way.
I agree.
Since nowadays things have changed with the technology and understanding, we know a lot about these things and matters. What do you think about this stuff?
Well, I think it's a really good point. I think it's a really interesting idea how you remember material and how you engage with it. So, obviously we've got a lot of science these days, a lot of technology, and we want to understand things in the most dispassionate way possible on some level. But I think there is also value in having a more, let's call it like cultural way of understanding things. It helps you connect with it on a more immediate level, and even on a metaphorical level. We have to carry something around in our brains. We can't carry all the model simulation results around in our brains with us. We have to carry some sort of conceptual models, and so I think it's about building conceptual models with different levels of complexity or different levels of technicality that serve different purposes. So, for example, sometimes I'll think about a thunderstorm cloud and I'll think about that like an explosion, kind of like like a big explosion going off. And, on a scientific level, it's not an explosion. There's no combustion. There's nothing sort of burning. But on a certain level, it sort of is like an explosion, because as the air rises and condenses, there's effectively, energy that's raising the temperature of the air. It's just that the energy is coming from condensation of the vapor rather than combustion. And I think if you think about a thunderstorm cloud as an explosion, that can carry you a long way in getting an intuitive feel for the way the process works.
So, if someone just asks you a very simple question, what is thunderstorm and what's the difference? How can we differentiate between that and any other kind of storm, and what makes it a little bit fascinating?
Well, I think that maybe taking a step back first, at its heart, everything is driven by the same laws, the same principles. It's all Newtonian physics, F equals ma, air and water, and the thermodynamics of water and air. And so we give different labels to different manifestations of those principles, but in many ways it's all the same thing. So generally when people talk about a thunderstorm as opposed to a hurricane or, like a mid-latitude storm, for example, generally what they're referring to is that explosive release of energy that comes from the condensation, which drives a narrow updraft. So a thunderstorm cloud is produced, or it's associated with a strong updraft, so strong ascending air that is about 2 kilometers wide on average. It's actually an area of active research why it's about 2 kilometers. The current paradigm is that there's a balance between how sleek the updraft is. So if you imagine a swimmer swimming through the water, if they're really sort of sleek and thin and streamlined, or maybe an aeroplane flying through the air, if it's a really sort of well-designed aeroplane, it's really streamlined, it can sort of slip through the air smoothly. But if it's really big and bulky, it kind of is going to get stuck, or it's not going to be as fast. So it's the same principle. That is what gives the updraft a preference for being small. The problem is if it becomes too small, then the warm ascending air, the sort of explosive air, that ends up just getting mixed out. So the air is also sort of mixing as it's ascending. And so if it's too thin, it just gets mixed out to nothing. And so it's the tension between those two factors that produce these updrafts. You know, it varies a bit around the world, but on average about 2 kilometers wide. So I'd say that's probably the key feature of a thunderstorm cloud, an individual thunderstorm cloud. There are other types of storms, you might say, like sometimes people describe a mid-latitude cyclone as a storm. Often with those sorts of processes, you're talking about ascent, sort of slow ascent of air that's happening on scales of like thousands of kilometers, and it's happening really slowly, and it's kind of just lifting a whole region of air very gently. The thunderstorm is much more violent than that. It's a small explosive updraft on a scale of maybe 2 kilometers across. Does that sort of distinction make sense?
Definitely. And there is the concept that I've just found the question in the internet. Someone was asking why storms are so common at the sea.
At the sea, I suppose one factor would be the moisture availability. So the energy that's powering those strong updrafts, like I said before, it comes from condensation. So when the vapor in the air changes from vapor phase to liquid phase, that's associated with an increase in temperature. And so that's kind of like the explosion. And so there's got to be some vapor in the air for that to happen. Now, if you're in the middle of the desert, there's not much water in the air because it's all sort of fallen out by the time it's gotten to the desert, and there's not much water there to evaporate. Whereas if you're really close to the sea, there's a lot of water there to evaporate. So that's one reason. There are other factors as well. So in the region that they call the Maritime Continent, which encompasses Indonesia, the Philippines, Malaysia, New Guinea, in that region, the thinking is that not only is there so much coastline, because all the islands are, I suppose, they're narrow in a sense. Their surface area is small compared to the coastline in a sense. Compared to a country like Australia, which has got a really huge interior, the islands of Indonesia are quite small. There's lots of different islands that all comprise the archipelago. And so the thinking is that there's so much coastline there that all the small-scale winds that occur because of coastlines, they actually contribute to the formation of the thunderstorms. And I can go into the technical reasons for that a bit more if you like, but that's another reason why you can often get more thunderstorms close to a coastline, because of the winds associated with the coastline itself.
Yeah, that's interesting. You see, based on different publications, actually, that around 2,000 people all around the world, globally, people died caused of thunderstorms.
Yeah.
And that makes it a little bit dangerous. And I think that can give us a little bit of an insight of why everyone should care about these stuff and these matters. And the question that I want to ask is that, what makes it so dangerous?
That's a good question. Let me think about how I'm going to answer that. I suppose the first response I'd give is to say, well, there are a lot of different hazards that a thunderstorm cloud can produce. So one of them is the rain itself, because there's such a really strong ascending updraft. You get a lot of rain forming in that updraft that then falls out. And so that can produce flooding very quickly. And so people can die from flooding, for example. There's also winds. So thunderstorm clouds produce very strong winds at the surface, and they do that in a number of different ways. One way is actually, if you think about maybe cooking in the kitchen, and if you were to tip maybe a plate of, or a spoon of honey, if you were to tip a spoon of honey onto the table, the honey sort of falls down under gravity, and then it spreads out horizontally under gravity. And that's a bit like what happens in thunderstorms, because there's all this rain, there's all this liquid water, and a lot of that actually evaporates as it's falling. And so evaporation is kind of the reverse of condensation, and so that actually cools the air. And so now you've got this huge blob of cool air which falls to the ground just like the honey, and when it hits the ground it spreads out horizontally a bit like the honey, and that can actually produce really, really strong winds at the surface that can knock down buildings and can knock down trees. And there have even been cases where crazy things happen, where the winds pick up material like shards of wood from broken trees, and that gets stuck in someone, like that gets stuck in their skin, and there's actually bacteria in the tree that then causes a really exotic infection. So that's actually happened a few times in the US. So there's all kinds of surprising ways that the thunderstorm can be impactful. I would say, however, that it's not the most dangerous atmospheric process. I think the leading one is still heat waves. If you look at just the fact that when it's really hot unexpectedly, I think that's still the most high mortality atmospheric process. I think the impact of thunderstorms can often be more economic. So the damage associated with thunderstorms can be extremely expensive. Certainly the costliest natural disasters in Australia tend to be related to thunderstorms.
That's a good one. And here's the funny thing, in terms of their complexity.
Yeah.
The to be predicted and all the kind of information, since your current work is actually developing computing programs that can help us, predict and all this kind of stuff. I don't know much about that, and you'll tell more about something that you're doing. But I have a question that I think people might think about this question.
Yeah.
Since most of the components that are available are caused, we can say, in the package of thunderstorms, like rain, strong winds, heavy hail,
all that
like
stuff.
That.
Yeah.
And the question is this: there is the issue of global warming now.
Yeah.
Is there any relationship between the global warming, the increase of global warming, which cause extreme weather patterns around the world, extreme climate, and the thunderstorm? Because different papers suggest that it is a little bit difficult to predict the trending. I mean, the occurrence, how frequent they occur, and all that kind of stuff. But since it's in the realm of atmospheric science, it's a realm of weather and all that kind of stuff, the question is that related to global warming? The increase, for example, just less than a month, US, I think, has been impacted with a huge thunderstorm. that happened in the US just like less than a month. Yeah? And there have been recurring situations, something similar like this in a different coastal regions all around the world. And the question is that this frequent occurrence, is it related to the increase for global warming? And if that is it related, how is that related to anybody else around the world? Is it because of an increase of a CO2 that caused global warming, that people pollute and all that kind of stuff? Is there any connection in between with this matter?
Yeah, it's a really good question. It's a very challenging question because I think if you look at, for instance, the IPCC reports, they'll talk about there definitely being lines of evidence, but I don't think there's a strong consensus yet on the relationship between thunderstorm frequency and severity and global warming. There's a few ideas people think about. Let me just think about this for a minute. I think it gets very technical very quickly. One thing that people talk about a lot, just to try to illustrate some of the complexity, people talk about a principle in thermodynamics called the Clausius-Clapeyron relationship. And this relationship... What's that, sorry?
What is that technique?
The Clausius-Clapeyron relationship, it tells you what the saturation vapor pressure is as a function of temperature. Now, again, that's a bunch of jargon, but saturation vapor pressure just means... And again, there's a lot of misunderstanding out there, I think, about this concept. Really, it tells you how much vapor there is in the air when there's more condensation occurring than there is evaporation occurring. So when there's net condensation, that's when raindrops are going to start forming and they're going to start becoming visible. But if there's net evaporation, it means that even though there's some condensation, there's more evaporation than there is condensation, and so nothing condenses overall. There's no raindrops that form. And so all the Clausius-Clapeyron relation really says is that the evaporation rate increases with temperature. And so to get net condensation, the temperature has to be higher. And so, again, boiling all this jargon down a little bit, in a nutshell, you can think about it as saying, as the air temperature gets higher, there's going to be more vapor in the air before net condensation can occur, before raindrops can form. And so what that means is if you had a parcel of air, just to make it concrete, if we had a parcel of air, say, today in Melbourne, and raindrops started forming in that parcel of air, and then we compared that parcel of air to another parcel of air, let's say in maybe 100 years' time, and let's say the temperature's 2 degrees warmer, when the vapor starts condensing in that parcel of air, there's actually going to be more vapor in that parcel if the temperature is 2 degrees warmer. And so you might take that principle and say, well, maybe that means that in the future there's going to be more surface rainfall because there's more vapor in the air when it starts condensing. And that might be true, and some of the models do say that's the case. The problem is that the processes are so complex, it's not a clear-cut cause and effect between saturation vapor pressure being higher and surface rainfall being higher, because maybe more rain evaporates in the warmer temperature, or maybe the air is less likely to become saturated in the warmer climate. So there's a few kind of hints that maybe surface rainfall might be more extreme or intense in the future, but it's really hard to nail it down because there's so many things that go into producing something like surface rainfall or hail. It's really hard to have any confidence. And so I think there's some consensus among the model simulations in some parts of the world, but I think overall it's very hard to say much with confidence at this point. I think my opinion, I guess, my personal view is that we're we're a little way off yet before we can say much with confidence, because I just don't think we really understand, even trying to predict thunderstorms in the current climate in different parts of the world. Even that's really challenging because we don't have a really clear-cut way to connect the environmental conditions with the intensity or the frequency of thunderstorms. It's just so complex. We have some good rules of thumb, some very, very good rules of thumb, but it's hard to be precise, I think, with this particular process. Does that sort of make sense?
It does. And there's something that I'm just having in my mind in here concerning thunderstorms and aviation turbulence.
Yeah.
When we are talking about aviation turbulence, what do we mean? Do we mean including those jet streams and everything? Or can you just explain a little bit concerning the aviation turbulence? What is it, and actually, is there any relationship between thunderstorms and in this?
Yeah, well, I think that I'm just starting in this field, actually, with this new job. But if you've ever flown, most of us have flown these days. If you've flown, you might have experienced the turbulence. The captain will say, "Oh, buckle in, there's going to be some turbulence." And
it is one of the things that I hate, or I am very scared, is when it's reached that part.
Yeah, the planes will bounce around. People do get injured from it. Again, I've
seen one, and it was actually pretty scary. There's a video online, actually. The guy forgot to buckle up.
Yeah.
The shaking was so intense, he found himself on the rope.
That's it.
Neck broken, something like that. Back pain and everything. And every time that I'm in that situation,
yeah,
I'm afraid.
Yeah, it is a bit scary. It certainly causes planes to crash. Thunderstorms are also either the main, depends on the airport, but it's either the main reason or the second biggest reason why planes can't land or can't take off, because of the risks and the hazards associated with thunderstorms. Regarding the turbulence, again, I think this metaphor of explosion is helpful here, because a thunderstorm cloud, it's such a forceful process. It's this big explosion, this big strong updraft. And if you think about, if you have an explosion, like a real explosion, you will hear it. For example, you'll hear it because the explosion is disturbing the air and producing sound waves, and those sound waves propagate through the air and reach your eardrums, and so you experience that explosion even though you might be a long way away from it. You might be able to hear it a long way away. And it's kind of the same idea in a way. The thunderstorm goes off with a big bang, but you don't hear it, of course, unless there's thunder.
Here's a little bit of a fact. I just find it online. It says, close thunders actually can reach a sound level up to 120 decibel, a threshold of a pain of a human.
Yeah, it's loud. What's interesting is the thunderstorm, it doesn't just produce a sound wave, it produces what you might call a buoyancy wave, which is just exactly the same as the waves you see on the surface of the sea. They might call that a buoyancy wave or a gravity wave. The difference is that you can't see it because in the air is what we call, I'm trying to avoid the jargon. It's stratified in the sense that the air gets lighter as you go up. And so just like on the sea surface, you sort of see the wave propagating on this interface between the water and the air, because the water is sort of denser than the air, and you can see that density difference. And so when the sea is pushed up in the crest of the wave, gravity tries to pull it back down, and that's what produces the propagating wave. It's the exact same thing in the air. The only difference is you can't see the density interface between the denser air, which is lower down, and the lighter air, which is higher up. But other than that, it's very similar. And so the thunderstorm goes off, and it produces these buoyancy waves that travel they can travel far away from the thunderstorm itself. And the thinking is it's really those waves that produce the turbulence that you feel. And so, yeah, it's not just a matter of flying around the thunderstorm. You have to fly a good distance around it, because even if you avoid the rain and the hail and whatever, you might still feel the waves.
Here, there is something that's just like common stuff. So we've talked about the turbulence and the relationship with thunderstorms.
Yeah.
If someone asks you a question, just a random question, over the course of history, we've heard plane disappear.
Yeah.
Some people sometimes ask you a question like, is there any kind of relationship, like thunderstorms opening a portal to another dimension, like plane disappeared or something like that?
Wouldn't that be fun? That's probably outside my ball. No. Look, like I said at the start, I think that thunderstorms are a pretty magical process, and they definitely spark human imagination. I don't think there's any science on portals at this stage.
Based on our current technology.
Based on our current theories, but look, we've got Higgs bosons and we've got gravitational waves. We've got all kinds of wild stuff in the natural. No, I'm being silly. I don't think so. I think that there is some thinking, if I remember right, there used to be this concept or this theory of the Bermuda Triangle.
Mm-hmm. They called it the Devil Triangle.
The Devil Triangle. And I think I read somewhere that that one reason it might be associated with disappearing planes and disappearing ships before we had planes is that it is a hotspot for convection, for thunderstorms. And that could be part of the reason. But I can't remember. Where is Bermuda? I don't know where Bermuda is on the map. Is it in the Caribbean?
It's actually closer between. It's just like a triangle trip between USA. I think there is the Caribbean or something. Let's just check one.
Let's have a look on the maps. Sure. I'm curious because it's such a. It crops up in Bermuda. Let's have a look.
Yeah, so Bermuda Triangle is on a region of the North Atlantic Ocean, roughly bounded by the southern eastern coast of the USA and the island of a great, I think it's just nearby Cuba, Hispaniola, Jamaica, and Puerto Rico.
Okay.
Just like a boundary, like a triangle trip.
Yeah, I don't know. It's probably more likely to be. Again, this is where the words start to get tricky, because in that region you obviously get a huge amount of what we call tropical cyclones or hurricanes. And I said before that a thunderstorm cloud is about 2 kilometers across.
And sometimes can produce up to 100 miles per hour, strong winds.
That's right. Whereas a tropical cyclone, that's more like 1,000 or more kilometers across. Now, a tropical cyclone, you might say, is comprised of thunderstorm clouds. It certainly includes thunderstorm clouds in the eye wall. And so often these larger scale phenomena, these extreme weather phenomena that we think about, they can represent things that are kind of built out of these individual thunderstorm clouds. That the metaphor might be like the Lego brick. The thunderstorm cloud itself, the 2 kilometer thing, that's a bit like a Lego brick, and you might build a much more large scale object like a cyclone. I'm simplifying it a lot here, but you might build a house out of those Lego bricks. It's a bit like that. So I reckon that Bermuda Triangle thing is probably more to do with tropical cyclones. But tropical cyclones do contain in them the thunderstorm cloud process. In some ways, you could view it as like a supercharged. It's like it'll get technical. Maybe I'll leave it there before it gets too technical.
It would be a little bit difficult to understand.
Yeah.
So, out of so many programs that we are using to measure, to predict, which one is the most common and the easiest one, and I think more accurate one, or we can say the more accurate technology we are using nowadays to study the phenomenon of thunderstorms?
Again, another really good question, and I've got to be careful I don't get myself in trouble here. I don't want to upset anybody, but my honest view is that the thing that has been phenomenally successful in weather forecasting is what we call synoptic scale simulations or synoptic scale models. And so when you see the weather report and you'll have the weather reporter saying, oh, we've got the high pressure thing coming in, and then we've got the low pressure on Tuesday, and then another high on Wednesday. Those are what are called, again, I'll strip the jargon out. Those are called large scale pressure systems. And those are the things that we can predict really well out to about 7 days. Now, a thunderstorm cloud, because it's a much smaller scale thing, and because it depends on whether or not condensation occurs, it's just inherently much more chaotic. And so really what you can do is predict the conditions in which thunderstorm clouds are more likely. And again, we can do that pretty well. But in my view, it's pretty much impossible to predict more than, say, an hour in advance exactly where the thunderstorm will occur. You might be able to say, and this is what the weather reports will say, they'll say, in Melbourne on Wednesday, high chance of thunderstorms, but that might mean the storm occurs in the CBD, it might mean it occurs in Gippsland, it might mean it occurs in Coburg. It's very, very chaotic in that way. The metaphor is a bit like if you're bowling, you swing your arm back and throw the bowling ball, and you know with pretty good confidence the ball is going to go down the end of the lane and it's going to go in the wherever it goes, the Bermuda Triangle void at the end of the lane. It's going to go in there. And if you're lucky, it'll hit some of the pins. But what the pins do is so chaotic because it's so sensitive to exactly where the first pin gets hit. It's really hard to predict how they're all going to bounce around with each other. And so it's very, very hard to predict the exact motion of the pins. Really, the best you can do is say, if you're really good at bowling and you're really accurate, you'll probably knock most of the pins over most of the time. And so that's kind of what we're doing at the moment with weather forecasting. We've got these synoptic scale models that say, yeah, we're pretty sure things are going to go off on Wednesday, but we know the ball is going to get to the pins on Wednesday, but the pins are going to bounce around like wild. We don't know exactly if it's going to be in Melbourne or in Eltham or in Albury or Wodonga or whatever. You know what I mean? Does that analogy make sense?
Yeah, it does.
And so what people do nowadays is they look at the synoptic models and they use the sort of principles that they know make thunderstorms likely, which is instability, which I can explain if you like later, and humidity and things of that sort, wind shear. And they'll say, okay, the synoptic model, the large scale model, which is really accurate, that's predicting all these things are going to be around Melbourne on Wednesday, say. And then you say, okay, there's probably going to be thunderstorms in Melbourne. That's the thing that I think is pretty good. Over the last few decades, we've been moving to, again, the jargon is convection permitting model. What that means is the model is now, the simulation is now so detailed, the simulation can produce its own things that look kind of like thunderstorm clouds. And again, it's really interesting. Just immediately, I said before, the thunderstorm cloud's about 2 kilometers across. most of the models that they call convection permitting, they use what's called a grid box. They use these grid boxes which are 4 kilometers wide, and what that meant, the grid box is like the resolution on your camera. It's sort of like saying, or the resolution on your computer, it's like saying, we're going to get all these grains of sand and we've got a photo of the beach and we want to be able to resolve the grains of sand and see them on the photo, but we've only got 4 pixels in our image. We've got 4 pixels across, 4 pixels up. So we've got 16 pixels in total. And so you take the photo of the beach and all you're going to see is a bunch of yellow and brown pixels, and it's like, you're not going to see the grains of sand. And that's kind of like the metaphor. The metaphor is the storms are about 2 kilometers across, but your computer image, that's the model, the pixels are maybe 4 kilometers across. And so sometimes, you will see storm-like things in the image and they'll behave in a lot of ways like thunderstorm clouds do, but in many other ways the physics will be completely wrong partly because, well, it's just way too big, it's just, does that make sense?
Yeah, it does.
And so I guess to round out that question, I would say this is part of why it's such an active area of research. We've had so much success with the large-scale models, and there's a lot of really good evidence that we're going to get increasing performance with the convection permitting models. We've got a lot of great stuff already from the convection permitting models, but in my mind, it's not completely clear yet just how much value they add beyond the traditional approach. They add some value for sure, but it's at this stage, I think there's a lot more to do, a lot more to go. So I think, the traditional weather forecast is pretty good. And I think if you want to know what thunderstorms are around right now, if there's one near you that's coming towards you, you can look at the weather radar.
And then you can have more information.
That's right, because that's not a simulation. That's just an observation. That's just saying, oh, look, there's one down the road. It's coming. I better get ready, Yeah. So that I think is, and that's what the weather agencies do. They use that combination of technologies to provide the warnings, to inform emergency services. They engage with all sorts of sectors of society. Now they even engage with the medical services, because when thunderstorms are coming, that can produce more asthma, for example.
Yeah.
So those are the combination of things, and I think that's what's reliable.
Definitely. And one thing that I want to say is, I believe there is a lot to learn about thunderstorms.
There is.
There is a lot of things that we can unpack from this learning and understanding it, though we are currently on this ongoing journey, understanding the natural phenomena and what actually they can be helpful in our world in so many ways. One thing that I understand is we've come along the way, and we've reached to the point that we understand what we are doing to this planet, and we are currently find a way that, okay, how can we balance? We've already damaged our planet, polluting it beyond what beyond. Sometimes there are other places can be even unlivable right now based on the pollution, living situation, and we've reached to the point and say, okay, this is the problem. We do have a problem. What can we do to make better? What kind of strategies and plans we can make better? Okay, fossil fuel is the problem. Let us shift to another source of energy. Let us try to find natural source of energy like solar energy, wind, hydro, and all that kind of stuff. And back in the days, I think in early, I think between 19th century or something like that, I don't remember quietly yet people started asking questions like, okay, is there any other way that we can come across and find a way to harvest the energy produced from lightings? Because we've seen that, okay, we are using, let's say, for example, the sun radiation, UV, which help us produce enough energy. And it can be quite helpful, but lightings are more powerful, produce more temperature. Probably there's something we can get out of it, and today it's not the current technology to do such a kind of stuff. It's not, we haven't reached that far, though someone tried over the years and still it's not successful. So what I can say is there are so many things that we want to learn. How complex the relationship between the thunderstorms, the increase in the frequencies and everything, because we are currently still struggling on predicting how frequent they occur, when they will occur, prediction and everything, because we are currently struggling. The only thing we have right now is an observation and currently dealing with models and everything. But it has to reach to a point where this knowledge bring light to the public. People have to understand, okay, where do I fit in this? You know, these are natural phenomena. Is there anything that I do increase the intensity of this phenomena, or something else that does this situation? Is it because I emit CO2 that cause global warming, that increase temperature, and the food, and if we can just say that the food that thunderstorm, like you said, temperature, moisture, temperature, and something like that, is there any relationship? Even though it's a little bit complex to put this thing together for people to understand, you know, but we are still in the progress of learning, and everyone have a role to play. And I do understand, ladies and gentlemen, this is just the beginning, and this season I will bring more people. We can answer more questions concerning the natural phenomena, and so as we can reach a level and say that, okay, based on our technology, with our understanding, probably this is what can be done. This is a little bit challenging. Probably we'll find a way to develop A, B, and C's so as to get E, F, and G. And there is a lot to finish. There is a lot to talk about. And unfortunately, today, it was just the beginning, the buzz of what is it, the thunderstorm. You've heard some fascinating story on how our ancestors all around the world eager to study and learn these things, learn the thunderstorm and everything, and reach to the point people liked it so much, afraid and terrified, they even gave them a title of probably this is the god of something. This is the god of rain and fertility. This is that. They had their own way of learning more about natural phenomena. We are so lucky with more advanced technology and everything, and yet we still are on a journey of learning and understanding these things. Until next time I'm pretty sure it will be more fascinating story, and I'm pretty sure I will bring Ewan back in here. You need to tell us more about climate extremes and in relationship with thunderstorms and everything. And I'll find another person. No, we'll find a way that to see, is there any possible way that we can harvest the energy produced from lightning and thunderstorms? Until next time, Simon William sign out. Bye-bye. Ewan, do you have anything else to say?
No, just thanks so much for having me on. It was a lot of fun.
Thank you for coming.
Pleasure. See you next time.
Until next time. Bye-bye.
Bye-bye.